Hello, everyone, and welcome to our webinar. My name is Marina Silva, and I'm representing Integrated Global Services. And I'm joining you here from England. And just so we know that you can hear us and you can see us, could you please type in the chat where you are joining us from today? And I'll get this started. Let's introduce our speakers. Today we have Larry Emch. Hi, Larry.
Hello, hello.
And we have Scott Donson. Hi, Scott.
Good afternoon, good evening, and good morning, wherever you are.
That's right. Good day. Good day.
Larry and Scott are our resident fired heater and furnace optimization experts, focusing on improvements in the convection section. That's where you go to Scott, and radiant section. That's where you go to Larry. And they will share their expertise with us with the help of two very specific case studies. The presentation will take about 20 to 30 minutes, and then we will have up to 30 minutes of live question and answers. And without further ado, over to Larry.
So I find myself today in the great state of Texas in a Fairfield Inn somewhere, and hoping for the best internet connection. My responsibilities at IGS are under the product line that we call thermal efficiency. In particular, two of the product lines. One is called C-Tech, and the other is Hot Tech. So I'll talk a lot about the C-Tech because that's really the major focus for today's webinar. And Scott, I'm glad you're able to help me on this today.
Welcome.
And Scott, where in the world are you?
I'm just south of Antwerp.
No.
Again, just like you, Larry, sitting in a hotel room
That's right.
this afternoon, enjoying the not so great weather here.
There you
It's
go.
a little bit brighter today, but rain follows me everywhere. Anyone who's met me usually got a rain cloud behind me somewhere.
Gotcha. Well, let's go ahead and start moving through the information. And if there are questions in the chat, please help me get to those. Then I'd also like to answer questions on the fly, just because sometimes those questions get lost at the end, and then you came to the meeting and didn't get all the information you needed. So I'll start with the classic topic, or certainly the topic that's most important today in the world. And let's talk about greenhouse gases, the protocol, because within that protocol, scopes 1, 2, and 3 are common knowledge, and most of the world is rightly so paying attention to how can we make a meaningful movement towards scope 1 in particular, because the beauty of scope 1, it's all about direct emissions. And we can make, with our product lines within IGS, we can make a meaningful difference in your next turnaround. And that's part of the beauty of these technologies. These technologies have been around literally for decades, 2 decades, and they've always had this advantage. They've always had this value proposition, but now it's even more impactful. It's let's say easier to justify. It's much more meaningful on the whole emission topic. And that's why I think it's important that we reintroduce these options and technologies to the world, because they're certainly well-heeled, well-developed, and ready to be implemented. Go ahead. There we go. All right, so let me say a word about IGS first, because I think that's an important perspective. Integrated Global Services is a collection of technologies that we have built over literally 2 decades. And here are 3 of the 5 that are most relevant today in what we're going to talk about. There's another product line called HVTS, High Velocity Thermal Spray, which is driven by corrosion, another big part of our business that can be very helpful. But we wanted to narrow it down. But my comment is probably most important in that all the technologies, including HVTS, are all homegrown. This is our own R&D effort with our staff, our engineers, and our people over many years. So all of the technologies that we offer, that we provide to you, we made them. We invented them, we developed them, and we refined them. No pun intended, sorry. So, but that's the beauty of having a relationship with us, is that we're the inventors, and in our business model, we're also the applicators. So you're talking to people at the beginning of the process when you're thinking about revamping, improving your situation. And at the end of the turnaround, when we have to have that all important meeting where you sit down with the plant and say, here's the money we spent, here's the value we got, and here's the proof of that data, that's part of our business model. So we are connected to you, or we're the bookends of the project. We'll prove it in the beginning, we'll evaluate it in the beginning, and then we'll prove it at the end. And I think that's a unique relationship that you can take advantage of, because it certainly is quite meaningful. Let's go ahead to the next slide. All right, so let's drill down on the CTEC conversation for now. CTEC is a variety of ceramic coatings. Literally, we've invented ourselves. Dr. Zhu is still on the staff and continues to reformulate. So CTEC ceramic coatings, it's sort of like leaded and unleaded. We have a category that's thin film for applying on metal coatings, for instance, radiant tubes. And this is a picture of a catalytic reformer. And we have another category, which are the high emissivity ceramics that go on all types of refractories. In either way, both of those coatings are really hand in glove in terms of applying them into high temperature heaters and furnaces, because they're a fantastic technology that allows you to lower emissions, meaning lower your CO2, use less fuel to manufacture the same barrels per day. And if you're in the great situation of having to increase throughput, it also gives you that flexibility. So you've got technology that will serve you no matter where the market shifts. Fuel savings, CO2 reduction, and NOx reduction automatically every day of the week. And if you can take advantage of a throughput, let's say you have a busy season, you can throttle it up and go. Great flexibility for years of coating life. So let's start with pictures. I always think that's a great place to go. What's going on with radiant tubes? In this case, we're talking about a catalytic reformer. It's a great furnace to talk about because it really captures the essence of what the coating does. Radiant tubes, we all know they've got on them. That oxidation is that process of oxidation is quite a headache. It creates headwinds year over year over year. In minor cases, it's just a nuisance, and you've got to turn up the burners at the risk of running out of bridge wall temperature limit. In extreme cases, in heavy fouling, where you're driving a big octane number like 101, 102, you're going to build scale quite a bit quicker, and it becomes really problematic in terms of you're going to run out of burner, you're going to run out of bridge wall temperature, and frankly, in those extreme conditions, you're losing wall thickness. So that event, everyone lives within the industry to greater and lesser degrees. We want to stop the event. And that's what coating will do for years. I mentioned extreme conditions. There are many customers that operate at the high end of their temperatures, their tube metal temperatures, especially if they're pushing octane. And what most people have learned to live with, and you don't have to, is that scale you're looking at, half of it is actually your tube. You're giving up wall thickness. So why would you let those tubes age prematurely when automatically the coating provides that protection over the next 6, 8, 10 years? So it's a great extreme example of where you can not have to replace tubes earlier, in addition to all the, go ahead, in addition to the fuel savings. So let's drill down on a case study. This is a recent job we did. We thought it would probably be a good story because it captures the whole picture of tube and refractory coating, because it works very well together. Go ahead. Obviously pictures inside the unit. By way of a starting point, this customer is Tüpraş in Turkey. Let's say a very close relationship with those folks at multiple sites. We work with their process engineer. When they're thinking about revamping, they'll routinely include us in their consideration and their topics to see what technologies can help them. In this case, it's exactly what they decided to do. Normal configuration, right? Straight through tubes. We can see 3 of the 4 cells here. 9 chrome metallurgy, the most common tubes that we coat every day around the world. Whether they're U-tubes or whatever the configuration, it's still absolutely appropriate. You can see the short division walls where you've got a lot of mixing up going to the convection section. Those division walls are all part of the refractory surface area. Go ahead. And it's an interesting conversation when you're close with a customer, and that's where they get the most benefit from our global experience, is that they talk to us about and shared this data about, we've got this bridge wall temperature headache. We've got this penalty that actually hurts us on production. And so we do know that if we do some sort of manual cleaning on the tubes during a turnaround, we can bring that bridge wall temperature down, right? We're bringing it down to 820 C after a turnaround if we do mechanical cleaning. And then they went on to say, but, for all those days and dollars that we spent in a year, or certainly 16, 18 months, you're essentially back to the same bridge wall temperature. The 857 bridge wall temperature is what came back in essentially a year. And that was disappointing to the customer for the time and money spent in the turnaround with manual cleaning. It really is lacking in its payback. So this is what also helped drive them towards putting ceramic coating into the equation. Instead of cleaning the tubes, let's lock those tubes into a new condition for the next 6, 8, 10 years. That's a much more meaningful payback to you. Scott, could you give me a show of hands that I'm coming through loud and clear? Great. Next slide, please. All right, so pictures always tell a great story. What do those tubes look like when we're starting in the turnaround? Obviously, you can see some scaffold poles and the like, and this is, typical tubes. You've got to put scaffolding in anyway in part of the heater if you're doing NDT testing, etc. Next slide, just to walk through the steps. Now we're going to clean that surface. These are very clean tubes. We've got them down to the right surface profile, the right cleanliness, because in any coating, you've got to have adhesion to the surface and cohesion to itself. This is that methodology for us. Next slide. Phase 2, now we're going to spray the coating on the tubes. Double fired tubes, we can spray all the way around. You want to cover as much of the surface area as humanly possible. Phase 3, you've got a coating that has no VOCs. It's water-based, so it's not quite cured yet. We're going to wrap those tubes up and protect them because step 2 of the coating is to spray the refractory surface. Remember, we've got both surfaces we're working with to improve the radiant efficiency. So wrap the tubes. Now we're going to spray refractory. We have different formulas because we have different adhesion expectations, different thermal coefficients we've got to deal with. So we maintain adhesion during expansion. So we've got coating for fiber refractory blankets and for brick, insulating fire brick, castable, etc. Different formulas, different performance advantages. Now here's the best part of this relationship. We had all this preliminary data, for instance, the first infrared image on the left, they're running that unit at 720 C. That's that starts to become problematic, and certainly those numbers can go up. You're also thinking about what's my actual tube metal temperature, looking at the tube surface temperature, and now we pivot over to what the coating did. So after the unit is taken up to temperature, after it's normalized and running as it should, post turnaround, those same tubes are now looking at 560 C. That's a huge win. If you're on the inspection team, you've got nice uniform temperature. If you're on the process team, you know what you've got in terms of your absorbed duty, something you can depend on for years to come because you don't have that scale creating headwinds. And that's where your fuel savings starts with, right there. You don't have to fire through that scale. And the scale won't be back for quite some time. So next slide, post-project again. This is data. Again, it all comes from the customer, and that's the beauty of it. You can see all this in Pi and all the other software that we use around the world. But your fuel firing, right? You can see on the left, 39 gigacals per hour, and now we're down by 5 gigacals per hour. A nice change, and a change that's going to be around for quite some time. And of course, you're thinking faster than I am. There you go. But the point is that previous slide was all about the data that the customer supplies us, and we'll do some post-coating calculations because that bridge wall temperature is no longer a production limit. You're not pushing too high of a temperature even into the convection section where frankly Customers have done inadvertent damage to their convection sections just by operating at those high temperatures. Next slide. And then it comes back to the data, right? We go back and recollect with the process team, our fired heater folks and yours. And what's the most important number? Apparent radiant efficiency. That is a fantastic win. When you think about a radiant efficiency increase of 6%, absolutely meaningful and something that you can depend on for years to come. So we do get into the numbers with you because that's important, right? Fuel savings, you've got to show it. That 13% fuel savings, you'll have the same percentage of CO2 reduction. Plus, the thermal NOx will come along with that. That thermal NOx, I don't know that number off the top of my head. I would expect it to be closer to 18, 20%. Next slide. So that's why the post-project analysis is so important. Just photographs, these are not from the actual job we've been showing earlier, but it does tell you exactly what it should look like when you open those inspection doors. You should know what your temperatures are. You should know how you're operating. You can see your flame pattern, do you have flame impingement, all the things that come into the safe and efficient operation of the heater. Next slide. And so at the end of the day, our report came back with a 13% fuel savings. And as I mentioned earlier, that beauty of having the ability to throttle up to a higher throughput, to be able to take advantage of even a seasonal production increase, or if a sister facility is not available and you have to pick up the slack. Now, or if you have the great problem of having to feed a BTX unit or paraxylene, you've got to kick up your octane, you can do it much more efficiently. So why not take advantage of a technology that is absolutely no risk and able to give you those kinds of benefits? There's the metric tons per year of CO2. Beautiful numbers, payback. Let's put it this way. Most customers see a payback of less than a year just on fuel savings. Sometimes it's half of that. If they're able to justify in a throughput, meaning they can take advantage of it, you're talking about months of a payback. 1 3-month busy season can pay for this project, and you've got those capabilities for the next 10 years. That's a win all the way around, at least in any internal rate of return discussions I've had with turnaround teams. That's really what you're trying to do, make the best business decision for how to spend the money in that turnaround with the internal rate of return expectations. And we can put all that payback calculations in front of you for you to make that decision. Next slide. And it's all based on your data at the beginning and at the end. So come back afterwards, and you've got a tube coating that's giving you protection from oxidation, protection from carburization, like new condition for years to come. And we can do follow-up infrared surveys just to show you that. And 10 years from now, 2 turnarounds from now, we can come back to you and do another assessment and make a recommendation as to what your next payback would be if you choose to recoat. Next slide, I think, will be on refractory coating. And that's where we talk about the differences. The refractory surface in most heaters, just by design, is relatively low. Let's call it 0.4, 0.6 emissivity. And we're going to vault that up to 0.9, 0.92. And that's where the unit was designed for X unabsorbed duty. We're going to increase that and give you additional capabilities and savings in terms of your throughput. So that refractory surface is really a secret gem for you. And in addition to that process improvement, if you've got fiber, and lots of them are because it's very efficient and affordable to build with fiber, we all know that fiber becomes friable over time. Even if you spray the industry standard of rigidizer on it, rigidizer, though will stiffen it up, is not built for those temperatures. Ceramic coating is, in fact, a long-term durable surface. So you're going to if you spray the fiber with this ceramic, you're stopping that let's call fiber is going to oxidize, become friable. And when it becomes friable, it's going downstream and plugging up your convection section. So every turnaround, you're replacing 10%, 20% of the fiber. You don't have to do that anymore. That's a lot of days in a turnaround. And you're stopping the collateral damage, if you will, of sweeping that friable fibers and et cetera downstream your convection section. So not only are you getting a process payback, but you're extending the life of the refractory. So fantastic wins for the overall health of the unit. Next. There we go. I think this is the time, Scott, where you help me out, and let's talk about the convection section.
Yeah, time for a quick handover here.
Thanks.
Because now
Thanks,
we move in. No problem. Because now we move up the heater and we go into the convection box. And we look at a case history here for my door in Egypt, where we were asked actually by the OEM, or I think this is Technique, to go and have a look at their heater and see what we could do in regard to debottlenecking the heater and removing the deposits from the convection area, taking them back to bare metal so that they could improve the heat transfer of the unit and remove the problem, basically. So on first impressions, we found quite a bit of debris inside the unit. It was fouled quite heavily between the fins. And the build-up there was down from the top of the fin, as you can see in the pictures, all the way down to the root of the fin where it meets onto the tube. And you can also see some images there straight afterwards where we've cleaned these fins back to bare metal, and you get a situation where we know from visual experience that that will return the heat transfer, because we can see physically there is no deposit there anymore. So the whole thing was about returning fuel efficiency. So we managed to get a fuel efficiency recovery in the region of 1.2%, which gave them an efficiency gain of 1.3 gigacalories per hour on the fuel. A 22-degree stack temperature drop is always a good indicator for us guys, because when we like to see that distinct stack temperature drop, us simple people, if we see a simple stack temperature drop, then we know that you're saving a lot of fuel. A 44-degree flue gas leaving the convection section temperature drop, and also a 64-degree radiant inlet temperature gain. So a win-win all the way around. And I'm told that the number that everybody wants to see is this 2,500 CO2 reduction, which again, people in the know will know more about that than me. So what happens with the ROV? It reaches, it sits on top of the coil simply, and it reaches down in between the tubes. So it doesn't matter on the pitch whether it's a triangular pitch or a square pitch. The cleaning arm actually positions itself exactly where we want it, down in between the tubes. So when you're thinking of the top row of tubes, you're thinking about second row, third row, fourth row. That's exactly where we want to be, and that's where we want to remove the deposits from. So it removes somewhere in the region of about 90 to 95% of all fouling on the coils or the banks, whichever you want to call them. It doesn't damage your refractory, so please don't go down the route of, oh, we'll lose our refractory, it'll get damaged. It doesn't happen. In fact, just using water as our motive force means that your refractory isn't subjected to any harmful chemical, which can damage the actual adhesion which holds the refractory together. We remove the man from the operation. One of the remits of using an ROV is that you can take the man entry situation away. So you take any operation with a person involved going inside a confined space away from the project, and let an ROV do it. If anything's going to go wrong in a confined space, let the ROV take the brunt of any problem. And our target is to reinstate your thermal efficiency and reduce your stack temperatures back to original design. There's a key, back to original design. But you always have to remember, we're looking to strive that little bit further. So we want to take you back to where you were on the day that you actually built the unit or had it installed. And that brings back also your original fouling factors. So whatever fouling factors were built into the unit and the longevity that they estimated you would get before you would notice those fouling factors have disappeared, that's what we want to bring back. So if you had a fouling factor which supposedly would last 10 years, then again, you should be looking at a 10-year period before you start to notice major fouling again, if all your other parts of the heater are working effectively and correctly. Again, another application here at Tupras Izmir, which is the one that I think Larry was speaking about a little bit earlier. We're working on this same heater, working in the convection box. We have a slightly different image there, but again, you can see here the amount of debris found inside the unit was actually, it was quite extensive, if I'm honest. The deposits were wet, sludgy, sulfurous, refractory, anything from burning of really poor fuel to other things around the area from coming in from the atmosphere. So it was quite a challenging heater to start with. Increased the challenge by the fact that there are actually fins in those pictures, surprisingly enough. So it was very heavily covered in deposits. Sorry, I've got just some questions down the side which have appeared for me. What is the material of the fins? Well, in the convection box, you don't have aluminium. The aluminium would disappear quite quickly. Most of these fins are a steel or stainless steel. You can pretty much do a dance on the fins. They are very, very strong, circa 2 millimeters thick. So they are very substantial and of a substantial material. So ceramic have very low thermal conductivity. Won't its coating on the tube? Sorry, that's a previous
Scott.
question.
Yeah, I'll come back to that. I missed that when I was talking. After you get to the end of yours, I'll come back around.
Yeah, okay, no problem. Sorry about that. So as you can see here, a couple of images from one of our animations, which show where the cleaning heads actually position themselves between the tubes. And this is optimized so that we can actually do the maximum amount of cleaning in the shortest amount of time. Time being of the essence, of course, when you're in the middle of a turnaround. We want to work as quickly as we possibly can because we know that time is not infinite, and all the time that you're down is costing you money. Now, these jets work on rotational or even just a forward firing basis, depending upon what sort of deposits and the design of the heater that we're actually cleaning. So if you want to flick on another slide, here we go. And here you can see the before and after stack temperature, I think it is. Yeah, stack temperature on the cleaning activity just from the convection box. Now, in all honesty, this is our client's image. They did actually publish. It was very good of Tupper's to publish a paper on this and advertise it in the process journals. If they'd have spoken to us, we'd have probably given them a little bit more information and some better pictures than they had. But now it's in the public domain. It was very good of them to publish on our behalf. Telling us would have been even better. So yeah, as you can see, the information down the side of this graph was given by Tupper's, not by TubeTech or IGS. Can we push on one, please? We get into the end. No, here we go. Oh, so, yeah, we are. Questions. We seem to have answered everyone here, Larry.
Well, I just pivoted over to the chat. I saw the question. Ceramic have a low thermal conductivity, right? It's surprising. Wouldn't that hurt the heat transfer on a radiant tube? Excellent direction to go in. I actually should have answered that in my discussion. It is correct that ceramics are really an insulator in many different industries, but those are at very different thicknesses. In this use, we're talking about 75 microns, right? The thickness of a business card. Fundamentally a different use. So is there a measurable insulation? Absolutely, but we know how to calculate that within our inspections. And so matter of fact, we have customers that use our coating to calculate not only their tube surface temperature, but their tube metal temperature, because a lot of us don't have much, let's say, confidence in the TIs, right? And the numbers we get, those TIs, you never have enough of them and they never live long enough. And so our coding can also be helpful in calculating that. Now, it's also important to say that every heater, every style of heater has its own benefits or uses of the technology. So in a steam cracker or in a steam methane reformer, those high nickel alloy tubes, you would not coat those. You would do a refractory coating, which you can have a tremendous process advantage, but it's not appropriate to coat the radiant tubes in a hydrogen reformer. So we look at every heater on their own benefit. Crudes and cokers and vacs, I mean, all of those let's move now to convection sections. All of those are fantastic benefits for the business that Scott operates on our tube tech side of the house, because nobody has the discipline to keep those clean, right? We all know there's a lot of wins to regain your process preheat, to protect your crossover temperatures, big wins, quick wins, and turnarounds by using our remote operated vehicle. Scott, I think I see some other ones here.
Well, the next one I think
cleaning
is,
is that it?
Is it applicable to steam crackers? I'm not quite sure where we're going with that, because certainly as a cleaning the convection section, yes, I don't have any problem with that. In fact, most of our work is on steam crackers for the convection box cleaning. So I'm assuming that's a little bit more directed towards you there, Larry.
That would go back to my answer on the steam methane reformers, steam crackers, ethylene furnaces. We would not coat the radiant tubes based on metallurgy, but every furnace has its own. Every family of furnaces, we have to make a unique decision, and we have experience with many heaters around the world, so we'll know exactly the right way. Go ahead, Scott. I think the next one will be for you.
Okay. How does your cleaning compare with chemical cleaning? Well, it's about being able to reach. The good thing about the ROV is it's designed specifically to sit on the tubes and reach down between them. So our technology is specifically built bespoke for cleaning of convection tubes, rather than a random method of being able to try and clean something. When you look at chemicals, you have to also consider, will the chemicals react with what it is you're trying to remove from the tubes? For instance, if the tubes are covered in refractory, it's pretty inert. So is a chemical going to attack that refractory? If it does, then it's going to attack refractory of the walls as well. So you could be in a lose-lose situation there. So we offer a service which will remove pretty much anything from the tubes without having to be detrimental and use any harmful chemicals. If you're going to use chemicals online, there are one or two legislations coming into place in certain countries which are trying to change that as well now by using chemicals online. Next one. How would the degree of cleaning of convection section to be decided before concluding cleaning activity? Well, we take pictures before and after. So when we first come to your project, our guys will take pictures of every level, every bank, coil, whatever you want to call them, down through the heater. So we start pretty much at the top because we like the gravity falls. That's a bit of a bonus to us. So we'll take photographs of the top coil and then drop down through the rest of the convection section before we even start cleaning. And then as we progress, coil 1, which we class as the top coil, that'll be cleaned and you'll be asked to inspect. After that inspection, again, we take more pictures. And if we can position the camera in the right angle, then we can take a picture right the way down through that coil. And you'll see pretty much every fin and every tube, depending on how deep it is. But in general, 5-6 rows of tubes can be caught on a digital camera without too much trouble.
Scott, thank you.
Thank you.
Any more questions for Larry and Scott? Actually, Larry, if you wanted to ask Scott a question about the ROV, what question would you ask?
Does it fit? Because there's so many different configurations, right, of convection sections.
Yeah, we're spending more and more time with the OEMs, the techniques of this world, the Lummus, the last one, the other one's gone off my head, Technique, Lummus. Help me out. Lindy, that's it. That's what I was doing. Foster Wheeler. I'm trying to remember them all then. We're spending a lot of time with these guys, actually re-educating how we would like to see heaters designed. And when they look at what we're saying to them, that everyone without fault, every one of them has said, "Oh yeah, that's pretty simple. We can incorporate that into the design. In fact, you're not really changing that much. You're just making us think about what we're doing." and the changes are minimal that we ask for. And if they do them in years to come, the heater will be designed ready and willing to go straight for an ROV clean with the minimum amount of additional access holes for cleaning. The tubes will be positioned perfectly in alignment with what we need, and the gaps between them will be okay as well. So it'll make just life so much easier for everyone, not only the cleaner, the humble cleaner, the OEM, but also, more importantly, the maintenance crews on site.
I think we'll pivot back to the ceramic if I see the next question. In the event of a tube leak, I assume radiant section, is it easy to remove the ceramic, and what are the complications? Yeah, great consideration there. Well, there's like 5 answers. I'm sorry. I'm going to try to get them sorted out. Not a problem removing the ceramic is really, though it holds up and is very tenacious in high temperatures, a flapper wheel can make a quick removal of the ceramic. So if you had to do a couple of tube replacements in the next turnaround after the coating's been on for 5 or 6 years, not a problem. Flapper wheel, get your distance between your welding and just go ahead and get right after it. Not a problem at all getting it out of the way. So tube replacement, things like that, very straightforward. What will happen to the temperature distribution of the radiant coil if coating is removed from it? It's inconsequential. The surface area is so small that it will not be an event for you. When you think about when you think about removing the coating from a weld seam, not an issue at all. By the way, if it were to be, let's say you had to replace 7 tubes because of some weird thing that happened to you, we could also go in that turnaround. When you replace those coils, you could just recoat those 7 full-length tubes if that was important to you also. But that's all part of a game time decision that we would make with you in terms of the relationship and how you're considering your revamp work, your replacement work, things like that. Like when you do NDT testing, right? You're going to clean it up and take a measurement. You wouldn't go back and touch those up with ceramic. It really doesn't really buy you anything in terms of performance of the heater. I think I got to the crux of something there. I hope that got to the crux of the answer.
Thank you, Cavallari. Thank you. So, you asked Scott a question. So, Scott, what question do you have for Larry?
You can't ask the Oracle.
Yeah.
No questions for the Oracle.
Actually, I did want to emphasize something, but there's one more question. I think it might be for you, Scott. Is there any list of requirements? I think that's a convection section question.
Okay, so is there any list of requirements to be considered in design if we make to ensure that your equipment fits in properly during maintenance? Yes, there are. I have a little list. If you want to get in touch with us, Hamid, I'll happily send over the list to you. You can have a look at it without any problem. It's the same list that I give out to all the OEMs when we have the discussion. It's sort of difficult to do retrofit, obviously, because it's some of them may need the intermediate tube supports altering, but certainly, yeah, just drop us an email and I will send that on to you.
Back to the takeaway. Oh, our new furnace is already equipped. Oh, yes, indeed. Not many of us have to suffer through a retubing of a furnace, which can be quite an event in your career. But we do get involved with new builds. Matter of fact, we're in the UOP Schedule A rebuild in terms of their specifications for both tube and refractory coating. And not only we just finished one for Phillips 66, because if you want to get the most duty out of that heater for an extended period of time, plus keep the tubes new for that same decade, what a great win that is. It really comes down to funding, right? Is that a CapEx fund? Is it a maintenance budget fund? How do you want to handle it? So it's an internal business decision. That's why our business model is built on giving you the business case for what the advantages are and what the payback is on that coating, so you can make those appropriate funding decisions for you. I think I answered. My other question was that you can You can consider each furnace has its own unique advantages. For instance, a hot oil treater, a de-asphalter, you wouldn't even think of as a candidate, but in today's world, if that unit's hitting its NOx limit, all of a sudden our refractory coating, and if it has the right convection section or a convection section, the combination of those two approaches can get you below your NOx limit, which might be a huge win nowadays, or more importantly, you can pick up 4% production and still be at your maximum NOx limit. So there's a lot of great answers that are specific to the heater itself and the headwinds you're facing. In some cases, in a vacuum unit, you're going to replace all the tubes and they're stainless. That can be a great win for coating the stainless tubes, for getting instant emissivity and the maximum throughput of that heater that you can't get without coating, because stainless steels are shiny, you got to get a patina, it takes 2 years to get blah, blah, blah. So every heater has we have some very unique answers to. So that's why when we come to a site, we want to throw the net out in a meaningful way and talk about production limits, and then pick off those heaters and give you your evaluation. Can single fire heaters? Yes, they can. And the helicoil configuration, of course, you're already picturing how problematic that can be in terms of how do we get a man in there? What are the dimensions? Can we get to the outside diameter? Is that even meaningful in the total benefit of the surface area? So that's exactly the drill down conversation we want to have with you, right? Maybe that whole helicoil is coming out in the turnaround, and what a perfect way to get access to everything. So there's 100 answers. Just let us have that conversation, and we'll tell you pretty quick. Go ahead,
I nearly managed to get in. Just popping back one, how long does it take to clean the convection section? Well, it depends on the size of your convection section, depends on the length of the bank, the length of the tube, the depth of the tube, how many tubes down, how many tubes across. 1,000 questions I have to ask. And I take all this information from your as-built drawings, and we build the picture up from there in our spreadsheet. And just to give you a rule of thumb, it's really don't take this as a serious answer, but we tend to look at probably 1 to 1.5 shifts per bank or coil. But believe me, there are a lot of things I have to take into account. So that is a very, very loose judgment on time.
Well, Scott, I can't think of a job we lost because it didn't fit in the turnaround either. And that's the same for ceramic coating. We're very efficient. We're talking about a minimum number of days. Working around the clock is pretty common in turnaround. So yeah, you're not going to walk away from this job because it took an extra shift.
No, and of course, what we'd like to know is what timescale we're actually allowed to have. Before even quoting, it's nice to know what timescales we can work with. And as Larry said there, we can cut the cloth to actually fit the job. We just need to know what it is we're working with.
And thank you, Scott and Larry. I think we don't have any more questions. Appreciate everybody's time today. And if you have any follow-up questions, you're welcome to email us or respond to the emails you received about this webinar. You will receive an email with the link to the recording. You are welcome to share that with your colleagues. We will also have it available on our Vimeo channel in about a week, which we can share as well. There's a few handouts in the handout section, so have a look before you go. The case studies, the white paper, and I'll just pop the link to one of the case studies in the chat now. This is published in PTQ Revamps this year's issue. And again, thank you all. Thanks, Larry. Thanks, Scott, and have a lovely day.
Thank you.
Please invite us. Please invite us to your facility. We'll do a great job. Thanks, everybody.
Thank you, everyone. Goodbye.